Hello. Hola. Sorry I'm a bit late. Good morning. Hope everyone's doing well. All right, we've got enough viewers. Let's go ahead and get started. All right. Get out of the way, cables. Come on, cables. All right, so this is going to be our last lesson on circular motion and gravitation. So we're moving right along here through the physics topics. Okay. Oh man, look at the weather has changed, and my knuckles, my hands get all cracked in the winter. My the skin is split, especially because I wash my hands a lot, so it's it's like extra dry. All right, so let's talk about what we discussed last time, just as a refresher. Last time we discussed the gravitational field. Okay, and the gravitational field is denoted by little g, and basically it is the acceleration due to gravity. All right, the acceleration due to gravity. The units of gravitational field are therefore meters per second squared. But when we're discussing gravitational fields, we typically would say that the units are newtons per kilogram. So 1 Newton per kilogram is completely equivalent to 1 meter per second squared. It's just sometimes you put it in a different unit to emphasize an aspect of it. So when you are writing the units this way, you're saying, I'm talking about gravitational fields. Okay. There's Newton's law of universal gravitation, which gives you an equation for the gravitational field generated by something. And it's big G times m over r squared. Okay, so in particular, the gravitational field that this mass is generating is weaker farther away from the mass, because as r gets bigger, the denominator gets bigger, which makes the gravitational field smaller. Okay. Big G is not equal to little g. Big G is the universal gravitation constant. Its value is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. It's an odd unit. Okay. And then what we did was we discussed what was I going to say? We discussed the gravitational force is little m times g. So what I want to point out here is that little m is the mass of the thing experiencing the gravitational field. Okay? Big M is the mass of the thing creating or generating the gravitational field. Now, of course, everything in the universe that has mass creates its own gravitational field and experiences gravitational fields from everything else. So it's kind of a matter of perspective, okay? If I want to know what is my mass, or what am I going to do in a gravitational field, then I would consider everything else to be the thing creating the gravitational field, okay? But if I want to know, and then this would be my mass, but if I want to know how am I affecting the universe, I would use big M as my own mass and little m as the mass of the rest of the universe. You get what I'm saying? So it's about perspective. Whose motion are we analyzing, and who is causing that motion? Okay. So this is the mass of the thing experiencing the gravitational field, and this is the size of the gravitational field that the thing experiences. Okay? So, what we're going to talk about today is basically orbits. Orbits of planets, orbits of moons, etc. So, the general shape of an orbit which we're not going to prove. Is a shape called an ellipse. Okay. So you might have heard about an ellipse in your math class. You know, it's like the equation of an ellipse is like c squared equals x squared over a squared plus y squared over b squared. So that's the general shape. So an ellipse is basically an oval. Looks something like this. And one of the things an ellipse has is it has two what are called foci or focuses. Okay, so there's two foci. All right, and so we're going to consider the general shape of the orbit of a light object orbiting a much heavier object. Okay, so in this case, because there's a much heavier object, the much heavier object doesn't really move at all. And it turns out that much heavier object will be in one of the foci of the ellipse. So for example, if this is the Earth in its orbit, okay, then the sun is not in the middle of the orbit. It's not right here. It's actually at one of the foci of the ellipse. So this is a bird's eye view of the orbit. So from directly above the solar system, the Earth is going around. The sun is not at the center of the ellipse. It's actually at one of the foci. Now, if we look at an ellipse, it has a long axis, which is called the major axis, and it has a short axis called a minor axis. Okay, and so for a circular orbit, the minor axis and the major axis are going to have the same length. Okay? But if we think about a really like an extreme oval, so maybe something that looks like this. So that here's a focus right over here. This one has the major axis is a lot larger than the minor axis. And so the technical term for that, basically the bigger the major axis is compared to the minor axis, we call that eccentricity. It's an eccentric orbit. Okay. Low eccentricity. If it's a circular orbit, because a circle is a special case of an ellipse. If it's a circular orbit, then this basically has no eccentricity. Okay, so planets, all the planets have orbits that are ellipses. Okay, but they are approximately circular. Okay, so they are ellipses. They are ellipses. They're not perfect circles, but they're close enough to perfect circles that we're just going to ignore the fact that they're ellipses. Okay, because the analysis of orbits in terms of thinking of them as ellipses is a lot more complicated than just thinking about it as a circle. Okay, so we're just going to assume everything has a circular orbit. All right. What kind of things have eccentric orbits? Does anyone know? Type it in the chat if you know something that has a really eccentric orbit. I'll wait. Let's use an astronomy nerd. Or am I the only one? Nice. Comets. Perfect. Yeah, comets have highly eccentric orbits. Excellent. A comet has an extremely eccentric orbit. That's why, if you think about a comet like Halley's Comet comes around something like every 75 years or something like that. And so the reason you can only see Halley's Comet sometimes is because Halley's Comet is spending most of its orbit out here, really far away from the sun. Okay? And when it's far away from the sun, a comet is basically an ice ball. And when the comet is far away from the sun, it's colder and it refreezes. Okay? When the comet swings down through the solar system and actually gets close to the sun, the surface of the comet starts to sublimate. And so there's all this outgassing on the comet, and it gets basically a cloud around it. And the sunlight reflecting off that cloud is what makes the comet look the way it does. Okay? So you can only see a comet when it has this giant cloud around it, because the cloud is much, 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 much bigger than the comet itself. Okay? And so the sunlight reflecting off of that allows us to see the comet. So the comet has to be warm enough where it generates this giant cloud that can reflect the sunlight, and then we can see it. When it's out here, the giant cloud refreezes onto the surface of the comet. We can't see it anymore. It's too small to see on its own. All right. So planets tend to have very low eccentricity orbits. Comets have highly eccentric orbits. And then you have things like moons. Moons are sort of in the middle in terms of eccentricity. Okay? So, That was just talking about orbits. I could talk about planets and stuff literally all day long, okay? When I was a little kid, I'll tell you a story. When I was a little kid, my grandma got me a book, got me 2 books. One book was on astronomy, okay? Actually, it was about astrophysics. I mean, this was like a book for children, but it had like a lot of information. Like that book, I went through that book so many times when I was a kid. And then there was a book on dinosaurs. So I got a book on dinosaurs and I got a book on astronomy. And I read them both just all the time, constantly, just going through again and again and again and just poring over this book when I was like 5 or something. And to be honest, most of what I know from about astronomy, the basic ideas, came from that book that I read when I was 5. You know, it's just funny to think about that. I really learned any like mind-blowing new concepts in astronomy since I was 5? No. Well, I mean, there's dark energy and dark matter. Those would probably be the 2 things. But other than that, it's like it all came from that book. The basic ideas. I mean, the math has been filled in, but and then on my dinosaur book, I picked my nose and I wiped the booger in my dinosaur book one day, and because it had a booger stuck in it, I didn't like that book as much, which I think pushed me away from paleontology and towards physics. It's all because of a booger. Okay? Think about that. I wouldn't be here teaching you today if it wasn't for that booger. All right. So let's talk about circular orbits. So for a circular orbit, you have a central body in the center of the orbit. Okay. So this is, I'm going to call this the central body. I've drawn it as a star. Okay. But it doesn't necessarily have to be a star. It's just whatever the central body is. So if we were talking about a planet orbiting the sun is the central body. If we were talking about a satellite orbiting the moon, then the moon is the central body. If we were talking about the moon orbiting the Earth, then the Earth is the central body. Okay? Whatever the central body is, it has a mass m, the margin m. Okay? Then, if we think about the satellite is going to have a mass little m, and it's orbiting at some distance, which we will call big R. Okay? So what we would like to do is we would like to calculate the period of the orbit. So what that's going to allow us to do is it's going to allow us to basically predict the length of a year, if you will. Okay? So here's what we're going to do. We're going to use F equals ma. So Newton's second law for the satellite. Now, because the satellite is moving in a circle, the acceleration is the centripetal acceleration. So it's m, and I taught you 2 versions of the equation for centripetal acceleration. And so the one we're going to use, since I'm trying to calculate the period, is not the v squared over r because that doesn't have period in it. We're going to use the 4 pi squared r over period squared. So that's the acceleration. The force is the gravitational force, which is little m g. Okay? So one thing we immediately notice is that little m is on both sides of the equation, which means that it cancels out. Okay? Little m is on both sides of the equation, and so it cancels out. So what that means is that the period of an orbit does not depend on the mass of the satellite. I'm going to write that down. That's important enough that I'm going to write it down. The period of the orbit depends on the mass of the central body, but not the satellite. Okay? So what that means is if we put two satellites in the same orbit, but they have vastly different masses, they're going to sort of maintain their separation. Okay? Now, on the next line, I'm going to plug in the formula for the gravitational field, which is big G times big M over r squared. And on the right-hand side, we have 4 pi squared r over the period squared. So one of the things you will notice here is that little m is canceled out, so it's gone. And then what I can do is cross multiply. Okay, and cross multiply. And what you get is big G times big M times period squared, so that comes from multiplying that over, equals 4 pi squared r. Now I've cross multiplied this r squared over, so now I have r times r squared, which is r cubed. So this is our main result for today. Okay, and it is called, I believe it's called Keplers Second Law. So there's this astronomer named Johannes Kepler. I just like saying his name like that, Johannes. And he studied the motion of the planets, and he came up with 3 laws. His first law was that planets orbit the sun in an elliptical shape with the sun at one of the foci. So basically, this statement right here is Kepler's first law. The second law is this one. Actually, he wrote a version of the law for an elliptical orbit, not for a circular. And in that case, r is changed to the semi-major axis. So the semi-major axis is half of the major axis. Okay, so that's how Kepler's law works in the more general case. And then Kepler's third law was basically talking about the speed at different points on the orbit. And the speed at different points on the orbit. And hang on a second, I just want to make sure. So, and then what Kepler's third law said was that planets orbit faster when they are closer to the sun than when they are far away. Okay, so basically, and same thing with comets. Comets are going really slow out here, and then they go faster and faster and faster as they swing past the sun. So it's kind of like pew, pew. So that's Kepler's third law. Of course, Kepler expressed it in a mathematical way. Okay, but we don't need to know what that is. For a circular orbit, the speed is constant for the entire orbit. Okay. All right. Suppose we had gone through this entire derivation. So we have mg equals m. But what if I didn't use this equation? What if I use the equation v squared over r? So the masses would still cancel, and I would have big G, big M over r squared equals v squared over r. And then I could solve for the velocity. Okay. And what that tells me is that the velocity of the orbit is the square root of big G times big M over r. So these are kind of our two equations for today. You should be able to calculate the speed of an orbit, and you should be able to use Kepler's second law. Now, Kepler's second law is extremely versatile. Okay. What if you knew? Okay. What if you knew the period of an orbit? And so getting the period of an orbit is pretty easy to do. Okay, all you need is patience, right? Because orbits might take years to complete. You don't even need to watch the entire orbit, right? You could just watch a portion of it and then extrapolate. But it does require some patience. So you need to figure out, if you know what the period of an orbit is, and you know what is the size of an orbit, if you know period and you know size of the orbit, you could calculate the mass of the central body. Okay? This is how we know what the mass of the sun is. Okay? No one has ever taken the sun and picked it up and put it on a scale to determine its mass. Okay? What they've done is they've looked at the satellites of the sun, and based on their orbital sizes and their periods, we can determine the mass of the sun. So this equation is basically a scale for stars. It allows us to determine the mass of stars, of planets, with great accuracy. Okay? So that's kind of cool. Alternatively, if we knew the mass of the central body, there's a really great question in the chat, which does that mean we can't measure the mass of something if it doesn't have a satellite? This is surely the most accurate way to do it. Other things we could do is we could say, for example, we could say, this moon is made out of rock, and I can see the type of rock that it's made out of, and I know the density of that rock, and I can see the size of the object, so I could use density times volume equals mass. But that tends to be not as accurate because you can only see the surface, so you only know the type of rock on the surface. And furthermore, because of pressure within the central body, the density changes quite a lot as you go from exterior to interior. So for example, the rock, even though it's the same type of rock essentially at the surface of the Earth as you have at the interior, the density of the rock in the center of the Earth is much greater because it's under high pressures. Okay, so it's not as accurate to just look at the thing, but you can get an estimate. All right. Of course, now let's say you work for NASA and you want to put a satellite in orbit with a certain period, okay? Then this equation, so, let's say you want a satellite. A great example of this is what's called a geostationary orbit or a stationary orbit. A stationary satellite has a period of 24 hours. So that as the Earth rotates about its axis, the satellite orbits with the exact same period. And so from the perspective of the Earth, the Earth is rotating, but the satellite is orbiting with you. And so the satellite always appears in the same location in the sky. That's called a stationary orbit. That's why it's called stationary, because the satellite does not appear to move. All right. And so stationary orbits are very important. And this would allow you to calculate how far up, what has to be the altitude of that orbit in order to make it a stationary orbit. All right. So we know we want the period to be 24 hours. We know we want, we know the mass of the central body, so we can calculate the radius that it needs to go to. So if you're a NASA mission designer, you're going to use this equation. If you want to know what speed does it have to achieve, how much fuel do you need to carry to get it up to the correct speed where it will stay in that orbit, you can use this equation. So this is really important stuff. Like weather satellites, for example. You ever see those images of hurricanes and stuff, and it's like the Earth is frozen and the clouds are moving across the surface of the Earth. How do they get that image? It's from a satellite in a geostationary orbit, okay? So that it's always looking at the Earth from the same perspective. So anytime you want to look at something and just focus on that, you need to use a stationary orbit. Otherwise, the orbits are going to be either faster or slower than the Earth's rotation about its axis. Another thing that uses stationary orbits are GPS. So GPS can determine where you are by basically locating several satellites that are in geostationary orbits. Okay? So by figuring out so there's a bunch of satellites in geostationary orbits that are GPS satellites. And if you can lock on to 3 of those satellites, you can triangulate your position on the surface of the Earth. Okay, that's how GPS works. Actually, I think it's 4 satellites. I think you need 4 satellites. So if you're a runner like I am, when you use your GPS to figure out how far you're running, the reason it takes time is because your watch is locking on to 4 satellites. And if due to weather conditions or something like that, it can't lock onto 4 satellites, then it's going to take longer for you to acquire GPS. All right. As you can tell, I can just talk about this stuff all day. But we might as well do an example. Let's predict the orbital period of Neptune. Now, Neptune, the radius of Neptune's orbit is approximately 30 AU. So what is an AU? An AU stands for astronomical unit. And it is equal to the average distance between the Sun and the Earth. Now, why do I say average distance? Because the orbit of the Earth is an ellipse, and an ellipse goes different distances. You know, if you are right here, you're close to the central body. If you're right here, you're far away from the central body. So it's the average distance. Okay, and that distance is 1 AU is equal to about 1.5 times 10 to the 11th meters. Okay. So saying that Neptune orbits at 30 AU is saying that Neptune is about 30 times as far away from the Sun as we are. Okay. And since Neptune is the outermost planet, that actually tells us sort of an estimate of the diameter of the solar system. So the diameter of the solar system is about 60 AU. Okay, that's if we say that the edge of the solar system is the outermost planet, which it's not really. All right. The mass of the central body is equal to the mass of the Sun, which is 2 times 10 to the 30th kilograms. It's the mass of the Sun. So, we can use Kepler's law to calculate the period. So we have GM, 6.7 times 10 to the negative 11. M is 2 times 10 to the 30th. Period squared equals 4 pi squared times 30 AU. So 30 times 1.5 times 10 to the 11th cubed. Okay? So this tells me that period squared is equal to. Now you got to be really careful typing this stuff into the calculator. Use lots and lots of parentheses so that you don't scientific notation. You know, if you're not really comfortable with the order of operations, you have to use a lot of parentheses or you're going to get the wrong answer. All right. Okay, so this gives me t squared equals 2.68 times 10 to the 19th seconds. Take seconds squared, excuse me, because it's t squared, so it's going to have units. So now I have to take the square root, and I get the period is 5.18 times 10 to the times 10 to the 9th seconds. That's not very useful. That doesn't really mean anything to me, okay? Let's convert it to Earth years. So 1 Earth year is 365 days. Convert it to seconds. It's 3.15 times 10 to the 7th seconds. 31.5 million seconds. So I'm going to convert it to Earth years. And we get that the period of Neptune's orbit is right around 164 Earth years. Really interesting, okay? So the amount of time it takes Neptune to complete its orbit is 164 times, roughly, because it's not exactly that because I'm just ballparking these numbers, and also it's an elliptical orbit. But ballpark, that's the... So you will live your entire life and unless there's some miracle drug that's created, you will live your entire life, and Neptune will not even go around the sun one time. All right? In fact, it might not have even gone around the sun one time since it's been discovered. I'm not sure when it was discovered, but that just kind of blows my mind. It's just so lonely out there at 30 AU. All right. Let's do one more example. Okay. And that is, what is the speed of Venus's orbit? Okay. So Venus has an orbital radius of approximately, and I'm just ballparking it, okay, about 0.65 AU. Okay. All right. So it's closer to the sun than Earth is. How do I remember it? It's that, Mercury is about a third of an AU. Venus is about 2/3 of an AU. Hey, speaking of planets, has anyone been looking outside and seen that Mars is incredibly bright right now? It's very close to the Earth right now, so it's really bright. And then also, Jupiter and Saturn are very close to each other in the night sky right now. So they're not actually close to each other because Saturn is way farther away than Jupiter, but they're sort of in the same direction in the night sky right now, so they're right next to each other. Should go out and take a look at that. So what is the speed of Venus's orbit? Well, I'm going to use this equation right here. So V equals G, which is 6.7 times 10 to the negative 11, times M, which is 2 times 10 to the 30th, divided by R, not R squared, but R. So 0.65 AU, 0.65 times 1.5 times 10 to the 11th meters. And then I want to take the square root of that. And we get 37,000 meters per second. Typically, orbits are stated in kilometers per second, so you divide by 1,000. So this is about 37 kilometers per second. All right. So that's a typical orbital speed, is in kilometers per second. Kilometers per second. Very fast. So 1 kilometer. Yeah. There's a comment in the chat about Pluto. I think Pluto was already demoted when you guys were born, right? I can't remember when Pluto got demoted, but I think you've lived your entire lives with Pluto being demoted. When I was a kid, Pluto was still a planet, and I have to say that when we did the New Horizons mission that flew past Pluto, I find Pluto to be really charming. I really love Pluto. Okay. Well, that's my lesson for today. I'll see you in the Zoom room.